Today in this lecture and video of graph theory, I shall discuss what is digraph. A digraph consists of a vertex set V and an edge set E such that each edge small e in capital E is associated with an ordered pair of vertices. So this is a digraph, that means directed graph. Here you see in this graph G, from V1 to V2 there exists an edge E1, and from V2 to V3 the edge E2 exists. But we cannot say from V2 to V1 the edge E1 exists. So this is a digraph. So here we are writing where U1 corresponds to the ordered pair V1 V2. So this is an ordered pair V1 V2. So that means from V1 to V2 there exists an edge. So we are giving the direction here. And here also from V2 to V3 there exists an edge. So we are giving the direction in this way. Okay, so this is a digraph, that means directed graph. Next is tree. A connected graph without any circuit is called a tree. So that means in the graph G there will be no closed structure. That is, the graph is without any cycle or circuit. So this is that means tree. Tree means no closed structure is there. That means for this one, this is not a tree. This is not a tree, but for this one, this is a tree. Okay. So next is binary tree. A tree in which there is exactly one vertex of degree 2 and each of the other vertices is of degree 1 or 3 is called a binary tree. So for this graph, this is the vertex whose degree is 2. One vertex is of degree 2, other vertex is either 3 or 1. So this is degree 3, 1, 2, 3, and this is 1, this is 1, this is 1, this is 1. So this is a binary tree. Next is theorem. A tree without n vertices has n-1 number of edges. So we shall prove this one. See, a tree with n vertices, n number of vertices, has n-1 number of edges. We shall prove this. We shall prove this using mathematical induction. Mathematical induction on n number of vertices. So in mathematical induction there are 3 steps. First steps for n equal to 1 or 2, n equal to 1 or 2, we shall prove this theorem. Second step, we assume the theorem is true for number of vertices p, suppose less than n. And number 3, we shall prove that for n number of vertices the theorem is true. This thing we shall prove, this thing we shall assume, and we shall prove that for n equal to 1, 2 the theorem is true. So here for n equals to suppose 1, when number of vertices is 1, number of edge is 0, so number of edge is 0, so n-1, 1 minus 1 is 0. That means this theorem is true for n equals to 1. Now for n equals to 2, there are 2 vertices. When there are 2 vertices, number of edges equals to 1. So now n-1 is 2 minus 1 equals to 1. So that means this theorem is true for n equals to 2. So that means for this part is over. For n equals to 1 or 2, we have to prove this. We have proved this one. Now assume. So we assume that the theorem is true for all vertices is less than n. That means the theorem is true for those graphs which contain vertices less than n, and we shall prove that this theorem is true for the graph which will contain n number of vertices. Okay. Now in a tree, suppose alpha is a path from A to B, and now suppose this graph contains n number of vertices, and for this graph there exists a path alpha from A to B, and this is the only path because for a tree if there exists another path it will be a cycle closed structure. So only one path exists. Now what we shall do, from T suppose we are removing the edge alpha, we are removing the alpha. Now when we remove alpha, we shall get two components one will be from with A, another will be from with B. Now the whole graph contains n number of vertices. So obviously this part contains less than n number of vertices, and this part also contains less than n number of vertices. These are the two components. This component contains less than n number of vertices, and this component also contains less than n number of vertices. So obviously this theorem will be true because we have assumed whenever a graph contains less than n number of vertices, the theorem is true. So that means this number of edges of this graph is n minus 1, n1 minus 1. Suppose it is n1. Suppose this contains n1 number of vertices. This contains n2 number of vertices. And number of edges of this graph according to this theorem is n2 minus 1. So the total number of edges of this whole graph is n1 minus 1. So the total number of edges of the whole graph is n1 minus 1 plus n2 minus 1, n1 minus 1 plus n2 minus 1, and plus this edge. That means plus 1. So minus 1 plus 1 cancel. So n1 plus n2 minus 1, and n1 plus n2 is nothing but n. The n minus 1. n1 is number of vertices of this graph, number of vertices of this plus this, the whole graph, n. n1 plus n2 is n. So this is the proof of the theorem. Okay. So here also you see we have written, we assume that the result is true for n equals to for k number of vertices whenever k less than n. We prove the theorem for t which contains n number of vertices. Let alpha be an edge in T with n vertices a comma b. Since two vertices in a tree are connected by one and only one path, so there is no path between a comma b. Alpha is the only path between a comma b. Let us remove the edge alpha. The graph T minus alpha is disconnected. So the graph T minus alpha, when you are removing this edge, we are getting this disconnected. Two components, say T1 and T2. And this contains suppose n1 vertices, suppose n2 vertices, and both n1 and n2 less than n. The whole graph less than the whole graph. So now this part theorem is true. So we have used n1 minus 1, T1 contains n2 minus 1, and then plus 1, this plus 1 has come for this alpha, for this alpha, this alpha, for this alpha, this plus 1 has come. So n minus 1, hence the theorem. Thank you.